This video is all about minimizing the cost of metal in making cans. But before that, let's have an overview of what cans are and its production. Cans are containers for the distribution and storage of goods. Cans are usually made of tin metal. Its manufacturing involves 6 major steps. The first step is cutting the blank. The process begins with cutting a long sheet of metal into a circle, called the blank. After the circular blank is cut, it is drawn or pulled up to form a cup. The second step is drawing the cup. The cup is transferred to a second machine. The cup undergoes drawing and the ironing process, which basically increases the height of the cup. Another punch presses up against the base of the cup, forming the inward bulge. The third step is trimming the ears. The ears are small ripples, which resulted from drawing and ironing process. For safety purposes, the ears are being trimmed. The fourth step is cleaning and decorating. After trimming the ears, the can is cleaned and then imprinted with its label. It is squeezed in slightly at the top to make a neck. The fifth step is creating the lid. The lid is made of different alloy compared to the body in order to be a stronger metal. The center of the lid is stretched upward slightly to form a rivet. The pull tab is inserted under the rivet and secured by it. The last step is filling and seaming. The can is held slightly tight to be filled with goods by the machine. After the filling process, the lid is added to the can. Now, you might ask, how do manufacturers minimize the cost of metal in making cans? To answer this question, let me introduce to you the optimization. Problems about maximum and minimum values are actually optimization problems. Optimization usually involves two equations. The first one is the constraint. A constraint is the quantity that is true regardless of the solution. It is usually the given condition that must be satisfied by the problem. The second one is the optimization equation. This is the equation which represents the maximum or minimum value. Its values always depend on the constraint. Optimization helps minimize the cost of metal in cans production by finding the dimensions of the smallest possible surface area of the cans. From the situation, the volume of the cans is considered the constraint because it is the given condition that must be satisfied by the manufacturers. Meanwhile, the surface area of the cans is considered the optimization equation because it represents the minimum value that the manufacturers are trying to find. Assume that the manufacturers are given with a volume of 1,200 milliliters cans capacity. The manufacturers have many possible dimensions of the cans. The first can has a radius of 4 cm and a height of 23.89 cm. The second can has a radius of 6.5 cm and a height of 9 cm. The third can has a radius of 5.76 cm and a height of 11.51 cm. If the manufacturers want to be efficient in terms of the quantity of metal used, then they will choose the third can. Among the three, the third can has the smallest surface area of metal used. The third can also has the minimum surface area of metal used, which means that no other possible dimensions of can with 1,200 milliliters capacity has a smaller surface area of metal used than the third can. And this becomes possible by solving for optimization problems. But how do we solve for optimization problem? To solve for it, 6 steps must be followed. Let's go back to the problem. Suppose a manufacturer wants to make a cylindrical cans. Each can must be able to hold 1,200 cubic centimeters or milliliters of liquid. Find the dimensions that minimize the cost of the metal to be used to make each can. So we know that the answer is 5.76 centimeters in radius and 11.51 centimeters in height, as the surface area produced is the minimum. But again, how do we solve for it? Before answering, let's assign the variables and identify the two equations. Let h be the height of the cans and r be the radius of the cans. As stated earlier, the volume, which is the pi r squared h, is equal to 1,200 centimeters cubed, is the constraint, while the surface area, which is the 2 pi r h plus 2 pi r squared, is the optimization equation. The first step in solving optimization problems is to solve for one of the constraints variable. In this case, we solve for h, which is equal to 1,200 over pi r squared. The second step is to replace the variable to the same variable in the optimization equation. So we replace h in the surface area, or our optimization equation, with 1,200 over pi r squared, and we get 2 pi r times 1,200 over pi r squared plus 2 pi r squared. The third step is to simplify the optimization equation. We cancel pi r and we get 2,400 over r plus 2 pi r squared. The fourth step is to find its first derivative. The derivative of 2,400 over r is negative 2,400 over r squared, while the derivative of 2 pi r squared is 4 pi r. So we get negative 2,400 over r squared plus 4 pi r as the first derivative. The fifth step is to find its critical value. We set the first derivative equal to 0 and then solve for r. We transpose negative 2,400 over r squared to the other side of the equation, giving us 4 pi r is equal to 2,400 over r squared. We then multiply both sides of the equation by r squared to cancel the denominator. We have 4 pi r cubed is equal to 2,400. We divide again both sides of the equation by 4 pi and find for the cube root of r cubed to solve for r. Using calculator, it will give us 5.76 centimeters as the value of r or radius. Substituting the value of r in the solved variable will give us 11.51 centimeters as the value of h or height. The last step is to check the critical values. We solve for the second derivative of the optimization equation. The derivative of negative 2,400 over r squared is 4,800 over r cubed, while the derivative of 4 pi r is 4 pi. So we get 4,800 over r cubed plus 4 pi as the second derivative. We then substitute the value of r in the equation. Again, using calculator, it will give us 37.68, which is a positive value. Positive value denotes that the obtained values are the minimum. We are assured that the dimensions that minimize the cost of the metal to be used to make each can are 5.76 centimeters and 11.51 centimeters for radius and height respectively. Some example of optimal cans are Del Monte's garlic and chili corned beef, Alaska sweetened condensed filled milk, and Del Monte pineapple slices. If you observe, the physical similarity of these optical cans is the diameter to height ratio, which is 1:1 or the same in measurement. Aside from minimizing the cost of metal in cans manufacturing, optimizing saves energy, as there would be no recycling of wastes involved. Consequently, the impact of manufacturing on the environment could be lessened. Math is truly a set of problem-solving tools. We just need to be aware of these concepts in order to understand and apply it for the betterment of ourselves, our society, and the world around us.